So can you hear me well? Can I start?
Yes. Okay. So it's my pleasure to invite for the talk Francesco Basso Basset, if I am not, if I correctly pronounce. He is a researcher from the physics department of Sapienza University of Rome. The talk is, the title of the talk is here, so please, you have, I think we have enough time due to our coffee break, so please.
Thanks for the introduction, and thanks to the organizing for having me here and for putting together this very interesting workshop. Today, I will talk you about the research that we are doing in our group in Rome, and especially I will focus on the part that deals with developing and using quantum dots as entangled photon sources for experiments in quantum optics and quantum communication. But first, let me acknowledge the group. I work in the nanophotonics group, which is led by the PI Professor Rinaldo Trotta, and I will show you the results, which are also due to many of my co-workers. I just mentioned among them Michele Rota, Davide Tedeschi, Emanuele Rocha, and Julia Neuwirth, but also our many international collaborators, starting from Jackie Ulins. I thank Professor Armando Rastelli, who yesterday gave a talk, introduced already many of the topics that I will touch, and also KTH in Stockholm, Paderborn University, and the Quantum Information Lab, also located here in Sapienza. So let's start with some motivation. We look towards application mostly in quantum communication, and we know that here the most established application is quantum key distribution. It has been shown consistently and convincingly that quantum entanglement and quantum mechanics can be used as a resource to share a secret key between two parties. And this is working, but there are still some current limitations, and the most recognized one is the distance limitation. While the no cloning theorem prevents eavesdropper to copy undetected quantum information, it also makes this technology not compatible with classical optical amplifiers. And if we look here, for example, for prepare and measure protocols in optical fiber, this limits secret key exchange to a few hundred kilometers. For sure, we can have point-to-point networks with trusted nodes, but can we do any better than that? And one solution is offered by quantum mechanics, and we can imagine that if we manage to share an entanglement resource between a node and a receiver, we can use this through the quantum teleportation protocol to transfer a qubit of information without having the photon travel the whole physical distance through. Now, if we are able to distribute entanglement, then a whole lot of other regimes unlock, and this is due to concept known as quantum repeater. Here at the bottom right, I show one of the most famous proposals for it, which consists of having an entanglement distribution chain based on an operation known as entanglement swapping plus quantum memories at intermediate nodes. However, this is still very technically challenging due to the fact that you need very efficient hardware blocks, namely entangled photon sources, best measurement devices, and quantum memories. And in this talk, I will focus on the first one, the entangled photon source. At the moment, the state-of-the-art technology is based on spontaneous parametric down conversion in nonlinear crystals. And while this is a very powerful and versatile technique, it suffers from an intrinsic limitation, which is the probabilistic generation mechanism, which means that sometimes you will get a photon pair, sometimes you will not get it. And if you try to increase the probability of getting a photon pair, then you will also increase the probability of having multiple pairs inside the same time window. And this is negative because as we increase the per generation, per pulse, per detection window, you incur in a trade-off in which the measured fidelity to a maximum entangled-based state decreases due to these errors due to multi-pairs. And while state-of-the-art implementations, such as the one in this work from the group of Jianwei Pan, can perform very close to this theoretical limit, many other implementations often perform much lower than that. So the question is, can we have something like a push-button entangled photon source? Well, quantum dots try to offer a solution to this. And these are semiconductor nanostructures. More specifically, these are heterostructures formed by two semiconductors with different band gaps, such that we can have nanometric three-dimensional potential wells in which we can observe discrete energy levels. And for this reason, these are also called sometimes artificial atoms, despite being formed by tens of thousands of them. And if we create an electron-hole pair inside a quantum dot, this forms a particle with a very strong Coulomb bond, which is known as the exciton, which can recombine emitting a photon. This photon emitting process can be tuned in wavelength by design, by changing the materials and also changing the dimensions of the dot. It can operate at very high rates, up to gigahertz, since the recombination process can be very fast, and it benefits from the semiconductor processing technologies. Moreover, this photon emission process is inherently resistant to multi-photon emission, and if excited resonantly, it can provide a physical process for deterministic emission. Finally, the quantum dot also offers a natural way to provide polarization entangled photons. If we create two electron hole pairs inside the quantum dot, we form a state which is so-called bi-exciton. And is it possible to prove that by the Pauli exclusion principle and for angular momentum addition rules, we can see that this the total angular momentum part of the bi-exciton wave function in the part that can interact with light actually resembles a maximally entangled Bell state. And this entanglement can be transferred to a photon pair, and we can move from this single particle electronic energy level to an energy diagram which shows the total energy of the system. And you can see that we have the bi-exciton state on top, exciton ground state, and the bi-exciton can decay radiatively by emitting two photons, and due to optical selection rules, the initial entanglement is transferred to the polarization state of the two photons emitted. As I said, this process is inherently resistant to multi-photon emission, and we can prove this by looking at with our Hamburg-Brown twist setup. You can see in this intensity autocorrelation that the probability of having two clicks at the same time at the output of this beam splitter is very low. We measured as low as 1 part in 1,000. But with superconducting low noise detectors, and it was shown even lower than that. It's also possible to excite this cascade resonantly. We can do it in a coherent manner so that we can observe Rabi cycles by changing the excitation power. And we can prove by intensity cross-correlation measurement that the fidelity of preparation of this process, defined as the probability that laser pulse impinging on the quantum dot in its ground state actually generates to a photon pair, it's very high. It's been as high as 94%. So very close to our deterministic on-demand physical process goal. Now, we have looked a bit more into more detail recently into this by looking at how the multi-pair emission changes by changing excitation power over different Rabi circles and the effect it has on the entanglement. And what we have seen is that if you keep the laser quite short, we use 10 picosecond, which is less than an order of magnitude compared by the still fast combination times of these emitters, then the multi-photon fraction of the emission at the source remains negligible, whatever the excitation power. And we have also seen here at the bottom, you can see the concurrence as a function of the excitation power, and this also stays constant with a negligible impact of multi-pair emission. We have no trade-off here of any kind. And the figures of merit of entanglement can actually be even higher with these emitters. And there are a few limiting factors. The most important one is that sometimes we have a splitting in the intermediate step of the cascade, which is due to anisotropies in the confinement potential. This is known as fine structure splitting, and it can introduce a phase which varies randomly with the recombination time in our state and mix it up in the measurement. But we do have ways now to control this by either improving symmetry in fabrication or even by applying external fields to change the electronic structure, such as anisotropic strain fields. And these allowed to demonstrate fidelities to a maximum entangled Bell state up to 98% up to now. Now, we can see that quantum dot is a source of highly entangled photons. It's very efficient in generation. One question is, though, how to collect the photons. And the challenge here is due to the fact that quantum dot is embedded in a highly refractive material index material, which means that it's difficult to get the photons out due to total internal refraction. And you can see here that in an unprocessed sample, these numbers can be as low as less than 1% for the single photon count rate. But there are several strategies to overcome this. Probably the most successful is the use of resonant microcavities, which have told single photon extraction efficiency very high, but even for the pair up to 65%. One last challenge is related to photon indistinguishability, which we know it's extremely useful, for example, using the Ongo-Mandel effect to photon interference sub-splitter. This can be used to perform a Bell state measurement, knowing that only if we will have two indistinguishable photons with the antisymmetric Bell state, we will have a double click at the two output port of this beam splitter. Now, for these quantum emitters, we know that if we use them, we look at two photons consecutively emitted in a single photon emission process, then we can get pretty high photon indistinguishability. This is not as high for the two photon cascade, and this is due to time correlation in the cascade related to the lifetime of the two transitions, which normal conditions limits you to about 67%. Now, this can also be improved with photonic cavities. We demonstrated values at the moment of 90%, but this is an active topic of research in the field. For our experiments so far, we have used this sample design from JKU and Linz, in which quantum dots are embedded between two distributed Bragg reflectors with a solid immersion lens on top, and we can get these very nice entanglement figures, low multi-photon emission, efficient generation, and a compromise in terms of extraction efficiency, which is about 10% for the single photon rate, and the figures of indistinguishability that I gave you before. So even if the sample development is going on, is it already enough to support quantum communication protocols? And the answer is positive. And I want to show it first in a protocol, which is the entanglement swapping, which I mentioned is very important for the realization of the memory-based quantum repeater. And this is an excellent benchmark because it requires all the ingredients. You need to have entanglement, you need to have efficient Bell state measurement, and you also need counts because this is a four-fold coincidence experiment. So how does this work? Well, you start with two entangled photon pairs and you take one photon from each pair and make them interfere, perform a Bell state measurement. Once you have the results, the other two photons, which were previously uncorrelated, will also be projected onto the same entangled state. So this is a sketch of the setup we used to test this. We excited a quantum dot twice in a row. We took photons from one transition and make them interfere beam splitter to perform the Bell state measurement, while for the photons of the other transition, we perform a 2-qubit quantum state tomography to check if they are in the expected polarization state. Just a quick picture of how the setup looks like in reality. And these are the results we achieved. Here on the left, you can see a density matrix of the two photon state, which has a fidelity above the classical limit to the expected antisymmetric Bell state. While these values are not extremely high, they are in perfect agreement with the prediction of our theoretical model, which takes into account the imperfection of the source, and mainly in this case, the interference visibility. Now, as I told you, there are already improvements in the literature which show that we can improve this performance by a lot, and we aim to do that in the near future. But some improvements can be done also at a setup level, and I want to briefly give you showcase this for quantum teleportation protocol. You can see that there are a lot of similarities. I mean, you still have the entangled pair, you still have the Bell state measurement. We just replace one Bell pair with a single photon in a specific polarization state. And what we did was to start with a subpar quantum dot, for which we realized with the same Bell state measurement as before, the protocol, and we got success rate below the classical threshold. But if we add polarizing beam splitter in the Bell state measurement, which is a well-known strategy to discriminate between two Bell state now, and this is the best you can do with linear optics, we also managed to remove accidentals due to copolarized photons and further improve the performance and now surpass very convincingly the classical threshold. We even tested the possibility to introduce a moderate spectral filtering with a bandwidth which is still twice the natural line width of these emitters. And we still managed to improve the interference visibility up to 80% and also improve the teleportation protocols. So I hope to have shown you that these quantum dots already can be used to perform quantum communication protocols. So for the next step, I want to go back at the beginning. So we talked about the application. The first application is quantum key distribution. And we wanted to do a test out of the lab, and we did this in collaboration with the group, the Quantum Information Lab group of Professor Fabio Sciarrino, in which we tested entanglement-based quantum key distribution. And we did it before using an optical fiber between two different rooms in a building, but then we also explored a free space optical channel between the two buildings of the physics department of the Sapienza main campus. And the idea is very simple. We have on the two sides two parties which perform measurements in randomly chosen polarization basis, and when they happen to select the same basis, they know they will get the same result. So they can add it as a bit to a secret shared key. When they select a different combination, they can use it to do a test of a violation of a Bell's inequality, which can allow to detect for eavesdropping. So this is how the first implementation of our free space channel looked like. We had a sender platform on the roof of one building and a receiver inside the lab in the other building. And we managed this way to successfully perform a quantum key distribution. First, we tried this in fiber, and then in free space, where we obtain a consistent violation of Bell's inequality. We had lower count rate due to still some optimization missing in the channel setup, but we also obtain a quantum bit error rate of 4%, which is on average, which is well below the protocol threshold of 11%. And recently we did some improvements on the setup. We added an active pointing system, which allowed us to do the same experiment, but this time over the length of up to almost 4 days, therefore enduring also daylight condition. We have even if we have a wavelength 790 nanometers, and even rain, with minimal impact on the performance of the protocol. Finally, we have plans to extend this text infrastructure also with not only to a link, but to a network with more nodes. And the first step we did in this direction was to test an hybrid 3-node network, in which we also added a spontaneous parametric down conversion source. And the scheme of the network is shown in this diagram in the middle. We have 3 parties, one at the middle, which performs separable measurements. And it is possible to demonstrate if we have 2 independent sources. Therefore, we can establish a violation inequality, which is called the bilocality inequality, that cannot be surpassed with a bilocal hidden variable model. And we were able to demonstrate a convincing violation of this inequality. So before concluding, I just want to mention that our group is also active in exploring other promising quantum emitters, being them other techniques to fabricate quantum dots, but also very interesting activities in looking into quantum emitters in 2D materials, which have low fabrication cost, high potential for positioning and strain engineering. And with this, I've concluded my talk. I thank you for your attention, and well, encourage you to ask questions if we have some time. I don't know.
We still have time, I think, before you took off a break, which is now. But first of all, I would say thank you for very interesting and well presented talk. And Andrei Semyonov, please, question.
Okay, so I can read it from the chat.
One question, please.
So I will read it myself. So thanks for the nice presentation. Welcome. I am wondering, can you control the wavelength and spectral width, not by adding spectral filters that will reduce the signal of the emitted photons? I presume this control is necessary for storing the photons efficiently in quantum memory. Well, that's an excellent question. The integration with quantum memory, with quantum dot source, is still preliminary. We can control the wavelength. There are, as I said, it can be controlled at the design level to begin with. So you can have, I briefly mentioned it, the dots we work with at 780 or 785 nanometers, which is good to, for example, integrate with rubidium, but also with some other new rare earth solution based on neodymium. And but it's possible also to explore other wavelength in the telecom. So wavelength meshing, it can be done in design and then fine-tuned, for example, by applying strain fields. So wavelength matching is not a problem. The spectral width matching is more challenging because usually our spectral width is in the gigahertz range, which is often very large compared to quantum memories. This does not mean that there are not possibilities to do this. There are some quantum memories that offer the possibility of store photons with a gigahertz bandwidth. And I know that there are groups which are actively working on the topic. But at the moment, this is still a work in progress, I must say. So this is a bit what I would say on the topic.
Okay, Andrei, do you have?
Yeah, thank you very much for the very nice presentation. I actually had almost the same question, maybe a little bit more details. So it's, if I'm not wrong, on your side 7, it seems you mentioned, this is just for reference, this is not necessary, because I also would like to ask you how good you could control mode shape from such emitters.
Okay, so wait a second, my presentation starts.
So for example, making Hong Kong Mandel experiment, yeah, and how good modes photons are almost the same, identical.
Yes, so well, the quantum key distribution experiment was favorable because it did not really require the indistinguishability, but this is of course very important. So I want to first do a brief distinction between what you can achieve with the quantum dot as a single photon source. Maybe I can even show. So there are some problems which are related to the fact that quantum dot is a solid state. It's in a solid state, so is subject to some mechanism, especially charge noise, which can cause spectral wandering. So as I said, there are different problems though. This is the normal problem which would affect the quantum dot as a single photon source. But you have to say that there are approaches which we didn't use, but they are based on putting the quantum dot inside a diode structure. And it is known that by applying an electric field is possible to reduce the charge noise. In some condition, it becomes it's possible to obtain practically Fourier limited lines. And very recently in the group of Richard Barton, this was used to demonstrate interference even of different quantum dots with very high values, which could be used to do experiments which require even multiple interference at different nodes. For example, I could imagine in boson sampling or this kind of very heavily interferometer-based experiments. So as I mentioned, though, the quantum dot cascade is an additional problem, which is related to the fact that each cascade is the fact that the two photons are correlated in time, because basically you have to wait for the first photon to recombine, and this well, at the very naive way you can consider it as a time dithering is actually a form of time energy entanglement. So the strategy here is that this limitation basically depends on the ratio of lifetime between the first transition and the second one. If the first transition can be made faster, then this number can be improved. And there are already some works in the literature with this photon bullseye cavity, which has said that they can already achieve this indistinguishability about 90% for the cascade. But as I said, this is still, I think, a work in progress in the field. I think it depends on your application, what you are most interested in, and yeah. So, yeah.
Okay, thank you. If it's possible, one more question.
Yes, sure.
Last question, very short.
Yeah, okay. About using these your emitters for quantum key distribution.
Yes.
I understand that here you have single photons, so maybe
yes.
Something, the technique, something like decoy state protocols are not applicable here.
Yes.
It seems, but so far, can you somehow compare so your protocol, so efficiency or quantum key rate, or
yes, so
decoy state protocol, and related to this,
Andrei,
I stop.
Okay, yeah. So I will try to be brief. So in our protocol, we use the entangled photons. So that's actually an Eckert protocol. efficiency at the moment are still low, I would say, because we are not able yet to reach the limit that can be obtained for SPDC. We are a couple, I would say, for this sample, it's a couple of order magnitude lower, but what has been published already in the literature would actually presume that we can surpass the limit. Concerning the Coy-state protocol, using quantum dot instead as a single photon source, for example, for BB84, would allow to avoid using the Coy protocol because of low multi-photon emission and actually go to, let's say to a BB84 and therefore try to prove an advanced compared to, for example, attenuated laser. And there is some work, for example, from the group of Tobias Huber, who recently published a couple of papers in which they really identify what's the limit there. You have kind of like a, and it's possible with the technology that it is, of course, it's much more challenging in this case to implement attenuated laser, but it would be possible to overcome the performance, and I believe this will be done in the near future, at least for with a proof of concept demonstration. Yes.
Okay.
Thank you very much.
Thank you very much.
Sorry for the long answer.
Interesting talk. We have to go for coffee break. We have 1 minute for this. So next speakers during this minute can try to check if it works.